You can feel the heavy rhythmic vibration resonating through the thick rubber soles of your work boots long before you actually see the blinding glow of the liquid metal. You are standing on a grated steel catwalk, suspended high above a dust-coated concrete floor, surrounded entirely by an overwhelming complex network of massive forced air pipes, colossal exhaust hoods, and heavy industrial machinery that seems to breathe on its own. The air in this space is thick and oppressive, carrying a sharp, undeniable metallic scent that is heavily mixed with the distinct acrid smell of airborne ozone and roasting mechanical grease. Directly below your vantage point, an unnerving river of molten iron flows steadily, emitting a brilliant, nearly blinding orange light that casts long, shifting shadows across the corrugated steel walls of the building. The radiant heat hits your face in aggressive waves, dry and absolutely relentless, threatening to singe your eyebrows. This is a sprawling industrial facility that demands a staggering capital investment of $2 billion just to break the ground, and once the internal fires are properly lit, they are precisely designed to burn 24 hours a day, 7 days a week, for uninterrupted decades. To intentionally stop the material flow is to actively court financial disaster. How do you keep a machine of this incomprehensible scale running without a single pause? That is exactly what we are going to find out today. My name is Ray, and this is Industrial Enigma. This is the channel where we go directly inside the places that build the modern world and meet the people who keep them running. We are not looking at a sterile light manufacturing assembly line today, and we are not walking through a highly automated climate-controlled shipping warehouse. We are stepping deep inside an integrated steel mill. Let us start with the numbers, because the numbers are what make this strange. The true physical and economic scale of an integrated steel mill is deeply difficult to fully comprehend until you are actually standing directly in the shadow of its towering infrastructure. We are talking about a continuous physical footprint that is appropriately measured in square miles, not in square feet or acres. The dedicated rail networks existing alone within the secured perimeter of the plant can easily span dozens of miles, operating entirely to move raw materials, intermediate stages of liquid metal, and finished heavy products between distinct processing zones that are separated by vast distances. Building a modern facility of this caliber from the bare ground up can easily require an initial capital investment approaching $2 billion, a staggering financial sum that perfectly reflects the immense mechanical and thermal forces constantly at play inside the gates. As an operator here, you are managing internal processing temperatures that routinely exceed 1600 degrees Celsius, handling physical weights where a single, ceiling-mounted overhead crane routinely lifts ladles weighing well over 300 tons, and consuming electrical power at a continuous rate that easily rivals the daily draw of a mid-sized American city. The integrated steel mill inherently relies on basic oxygen steelmaking, the specific metallurgical process that blows high-purity oxygen at supersonic speeds through a bath of molten pig iron to aggressively lower its carbon content and create structural-grade steel. This precise, violently energetic process is the actual beating heart of the global industrial supply chain, successfully turning raw earth pulled from open-pit mines into the resilient material that builds urban skyscrapers, suspension bridges, and the massive reinforced hulls of transoceanic cargo ships. Facilities of this magnitude are towering monuments to heavy engineering and logistical perfection. Consider Gary Works, the massive facility operated by United States Steel on the southern shore of Lake Michigan. Gary Works operates an integrated steel mill on a scale that completely dwarfs entire neighboring municipalities, heavily shaping the regional economy, the local labor market, and the heavy shipping traffic all around it. The daily logistics required to simply keep the raw materials steadily flowing into the massive storage yards of a plant like that represent a singular triumph of continuous, unending scheduling. Every single day without fail, massive river barges, mile-long freight trains, and heavy bulk cargo ships arrive at the docks carrying thousands of tons of raw iron ore, specialized metallurgical coal, and crushed limestone. If you travel to the other side of the country, you will find Edgar Thomson Works, the historic mill located in Braddock, Pennsylvania, which has been producing steel continuously for generations. A massive integrated steel mill like Edgar Thomson Works routinely produces heavy steel slabs that directly feed manufacturing and fabrication chains across the entire North American continent. These specific places are not just factories in the traditional sense. They are entirely self-contained, breathing ecosystems, operating entirely with their own internal industrial logic, their own specialized emergency response teams, their own private rail companies, and their own dedicated utility grids capable of handling massive surges in power demand. The unique combination of these staggering numbers, the billions of dollars in capital, the thousands of degrees of heat, and the millions of tons of heavy material, creates a deeply unique and unforgiving operational environment. It is highly unusual because there is absolutely no margin for a system-wide utility failure. A catastrophic, unplanned plant shutdown does not just cost money in terms of lost daily production. It can literally cause the liquid metal to permanently solidify inside the massive processing vessels. A devastating plant-killing scenario that can take many months and hundreds of millions of dollars to physically cut apart and repair. The entire sprawling complex is a delicate, high-wire act of thermodynamics and continuous material flow, engineered from the foundations up to never stop moving. The internal physical architecture of the integrated steel mill is strictly dictated by the unyielding laws of gravity, extreme heat, and the sequential linear flow of the heavy metallurgical process. The long journey begins out at the raw materials yard, where towering mechanical bulk reclaimers slowly crawl across mountains of black and red earth, feeding the hungry blast furnace via an endless covered rubber conveyor system that stretches for miles. The blast furnace itself is a colossal towering vertical cylinder, thickly lined on the inside with specialized refractory lining, a heat-resistant brick that protects the structural steel shell of the furnace from the hellish melting temperatures raging inside. An experienced human operator standing down at the cast house floor at the base of the furnace, safely shielded behind thick, heavy protective glass in the climate-controlled control pulpit, carefully watches as the glowing, molten pig iron is finally tapped directly from the bottom hearth. The liquid iron flows swiftly down open, refractory-lined runners cut into the floor, throwing off a fierce, aggressive radiant heat that you can physically feel burning against your skin from 30 feet away, before heavily cascading down into massive, brick-lined torpedo cars waiting patiently on the heavy-gauge rails directly below. Those specialized torpedo cars then transport the glowing liquid iron across the plant grounds to the basic oxygen furnace. The massive steel vessel is physically tilted forward by massive hydraulic drives, and heavy, jagged scrap metal is charged into it from a crane with a thunderous, earth-shaking crash, immediately followed by the pouring of the liquid iron, which erupts into a localized firestorm of sparks and thick smoke. A specialized water-cooled lance is then lowered from the ceiling, injecting pure oxygen directly into the molten bath at supersonic speeds to ignite the carbon. The primary operator sitting in this specific pulpit relies heavily on massive banks of digital monitors, live camera feeds, and real-time chemical analyses to determine the exact perfect moment the violent blow is complete. The basic oxygen steelmaking vessel then immediately feeds the liquid product into the ladle metallurgy furnace, which carefully refines the chemical composition to meet exact, highly specific customer specifications before the molten steel is finally ready for continuous casting. Precious alloys are precisely added by the pound. The internal temperature is perfectly homogenized by stirring the liquid with argon gas, and the structural steel is perfected. From that refining station, the massive ladle is hoisted straight up by an overhead crane and moved carefully over to the continuous casting machine. The heavy liquid steel pours downward into a specialized tundish, which acts as a thermal reservoir to ensure a steady, completely unbroken flow into the oscillating, water-cooled copper molds below. The human operator stationed here stands out on the vibrating casting deck, wearing heavy, uncomfortable flame-resistant clothing and a highly reflective gold-tinted face shield, actively managing a continuous creeping ribbon of red-hot, solidifying steel as it moves downward through the massive water spray cooling zones. Finally, the glowing solid steel slabs forcefully enter the rolling mill. The sheer physical scale of the heavy machinery bolted to the floor here is immense. Massive high-voltage electric motors drive the hardened heavy steel rolls that aggressively compress and elongate the glowing slabs, flattening them out and turning them into thin sheet coils or heavy structural plates. The concrete floor shakes violently with a rhythmic pounding vibration as the heavy steel passes back and forth through the stands, loudly shedding brittle layers of oxidized scale before finally moving down the long run-out table to slowly cool in the ambient air. To the untrained eye of a casual visitor, an integrated steel mill looks exactly like a brutal, aging relic of the late Industrial Revolution, a chaotic, dirty environment defined entirely by open fire, venting steam, and heavy rusted iron. But that initial visual perception is entirely wrong. Hidden deeply beneath the layers of black soot and the massive, heavily bolted structural beams is a hidden layer of highly sophisticated, cutting-edge digital architecture. The modern heavy plant is essentially a massive, interconnected sensory network, The level of predictive algorithmic maintenance happening silently behind the scenes is exactly what keeps the initial $2 billion capital investment financially viable. Thousands of ruggedized digital sensors are permanently embedded throughout the heavy machinery, silently monitoring minute vibrational frequencies in the massive rolling mill gear drives, meticulously tracking the thermal signatures of the refractory lining inside the vessels to detect dangerous thin spots, and accurately measuring hydraulic fluid pressures in real time across miles of pipeline. The primary control rooms located throughout the facility look much more like modern aerospace monitoring stations than they look like traditional dusty factory offices. Complex machine learning algorithms analyze the massive streams of operational data continuously, constantly looking for the microscopic, invisible anomalies that indicate a massive steel bearing is just starting to wear out, or a critical water cooling line is slowly losing internal pressure. The reliability engineers and maintenance technicians actively use this data to carefully schedule targeted, precise physical interventions during brief, highly planned maintenance windows, safely replacing critical components just hours before they fail. They are no longer merely reacting to sudden breakdowns. They are actively anticipating them using pure mathematics. It is this invisible, comprehensive net of digital data that actively prevents the massive catastrophic failures that would otherwise bring the continuous flow of liquid metal to a grinding, permanent halt. You will routinely see dirty, grease-stained mechanics wearing full protective gear while holding ruggedized military-grade tablets as they walk the shop floor, actively cross-referencing live wireless sensor data with the physical, screaming reality of the machinery in front of them, diagnosing complex mechanical problems directly through the deafening noise and the blistering heat. And honestly, that detail is more interesting than it has any right to be. Now let us look at the small things that turn a massive industrial plant into a place where regular people spend the majority of their adult lives. First, there is the silent, highly structured visual language of the standard issue hard hat. The overlapping layers of stickers gradually accumulated on a protective helmet act as a highly visible, instantly readable resume, silently telling everyone on the busy floor exactly how long a person has been around, which specific, grueling maintenance outages they have successfully worked through, and exactly which departmental safety milestones their specific crew has achieved over the years. A perfectly clean, brilliant white hard hat instantly marks a person as a vulnerable newcomer, while a battered, faded, heavily scarred helmet, completely covered in overlapping, barely legible Union decals, commands immediate, unspoken respect from across the room. Second, there is the sacred, highly guarded ritual of the shift handover. Exactly 10 minutes before the hour strikes, the tired outgoing operator and the fresh incoming operator stand closely, shoulder to shoulder, directly at the main control console. It is a quiet, intense conversation, pointing carefully at specific glowing monitors, quietly noting a particular hydraulic valve that is sticking slightly on closing, or heavily warning the next guy about a notoriously bad, unpredictable batch of scrap metal that just arrived from the yard. This direct interpersonal exchange of undocumented, highly tactile knowledge is exactly what keeps the volatile chemical process stable from day to night. Third, there is the absolute necessity of the thermal isolation of the lunch break. In a harsh physical environment deeply dominated by extreme radiant heat, finding a cool, quiet, isolated place is practically a survival essential. The designated break rooms are heavily air-conditioned, positive pressure sanctuaries where tired operators quietly eat cold sandwiches from battered, heavily insulated plastic lunchboxes that have somehow survived decades of brutal shift work. Fourth, there is the heavy reality of the boots left permanently behind. Heavy, steel-toed metatarsal guardwork boots, deeply and permanently stained with black graphite, hydraulic oil, and gray dust, rarely, if ever, make it back into the clean environment of the family home. They are purposely left behind inside the massive steel lockers in the changing room, serving as a very physical, strict boundary permanently separating the dirty, heavy industrial world from peaceful domestic life. Fifth, there is the highly specialized, hyper-local vocabulary that outside contractors cannot easily decode. Veteran workers speak rapidly in a dense shorthand of technical terms and plant-specific historical nicknames, referring casually to specific rusted catwalks, problematic steam valves, and massive machines by strange names that have been handed down verbally through generations of rotating crews. Sixth, you will find the beautiful reality of the highly customized, permanently altered hand tools. Walk slowly through any of the localized maintenance shops on the property, and you will inevitably see massive wrenches and heavy steel pry bars that have been intentionally heated with a torch, bent at bizarre angles, and welded into highly specific shapes by the master mechanics, perfectly designed to reach that one specific, totally impossible retaining bolt located deep inside the continuous caster. Finally, there is the profound, quiet respect of the retirement walk. When a hardened veteran of 30 years finally finishes logging their very final scheduled shift, the entire crew silently lines the painted yellow walkway leading toward the main exit, firmly shaking hands and sharing very quiet, personal words of luck. It is a deeply profound, moving acknowledgement of sheer physical survival and unyielding dedication in an environment that demands absolute, unwavering focus every single minute of the day. Now, this would not be an industrial enigma video if we were not completely straight with you about both sides of this life. The everyday reality of working continuously inside an integrated steel mill is deeply, inherently demanding, and it takes a very real, compounding physical toll on the human body over the long span of a 30-year career. The physical environment is simply unforgiving by its very nature. The ambient radiant heat during the brutal summer months, especially when standing anywhere near the tapping floor of the blast furnace or up on the charging deck of the basic oxygen vessel, is physically exhausting and constantly threatens severe dehydration. The unrelenting, deafening ambient noise constantly generated by the massive forced air systems, the warning sirens of the overhead cranes, and the heavy grinding machinery requires mandatory constant double hearing protection just to prevent permanent deafness. Unpredictable shift work, constantly rotating backward and forward between bright days and dark nights, severely disrupts natural sleep patterns, ruins digestive health, and demands heavy, unfair sacrifices from spouses and children waiting at home. The true inherent danger of moving thousands of tons of liquid fire cannot be entirely engineered away. The Bureau of Labor Statistics, the principal fact-finding agency for the federal government in the broad field of labor economics and statistics, closely tracks fatal and non-fatal injury rates across the entire industrial sector. And the historical data consistently shows that primary metal manufacturing requires relentless, completely uncompromising safety oversight just to keep workers alive. The daily margins for error are incredibly slim, and the permanent consequences of a momentary lapse in focus are often incredibly severe. The Occupational Safety and Health Administration, the federal agency that has regulated American workplaces since 1971, fiercely enforces strict, complex guidelines over every single aspect of the heavy material handling process. For example, the Occupational Safety and Health Administration aggressively mandates the overhead and gantry crane standard, which dictates strict, uncompromising operational parameters and daily inspection routines under federal regulations to actively prevent dropped loads and catastrophic rigging failures. Furthermore, the entire domestic steel industry is currently dealing heavily with the compounding, difficult challenge of a rapidly aging, retiring workforce. Many of the very best, most experienced operators, electricians and millwrights, the specific people who deeply know the unique, hidden quirks of the aging machinery by sheer sound and vibration, are reaching full retirement age and walking out the door, leaving behind a massive, critical knowledge gap that is deeply difficult to effectively fill with new, inexperienced hires. Any veteran currently standing on that concrete floor will look you in the eye and tell you the exact same thing. The job is physically and mentally hard. It asks a massive amount of your time, and it changes you. But the heavy industry is currently heavily invested in actively mitigating these severe risks, spending millions engineering out the absolute most dangerous manual tasks with remote automation, drastically improving basic ergonomic conditions, and fiercely enforcing a modern safety culture that is far more rigorous, strict, and unforgiving of taking dangerous shortcuts than it was just 30 short years ago. The traditional, sprawling integrated steel mill fundamentally faces a massive, unavoidable technological transition in the coming decades. The intense global push toward industrial decarbonization is heavily forcing the entire heavy metal industry to completely rethink the fundamental way it operates at a chemical level. The absolute, centuries-old reliance on burning metallurgical coal to reduce iron ore is currently being heavily challenged by the rapid, massive rise of the electric arc furnace, a totally different technology that efficiently melts recycled scrap steel using high-voltage graphite electrodes instead of aggressively refining raw iron ore with carbon. While the modern electric arc furnace generally has a much smaller physical footprint and can theoretically be fully powered by expanding renewable energy grids, it currently depends entirely on the unpredictable regional availability of highly sorted, high-quality steel scrap. However, the major global players in the industry are actively investing billions of dollars into scaling up direct reduced iron technology, and they are deeply exploring the future potential of using clean hydrogen gas as a primary reducing agent in the massive blast furnaces, actively attempting to strip the heavy carbon emissions out of the primary steel-making process entirely. Alongside this massive environmental and chemical shift, advanced industrial automation continues to rapidly change the fundamental daily nature of the actual human work. Heavy, shielded robots now routinely handle the absolute most hazardous manual tasks, like taking manual temperature probes directly from the molten bath, or physically skimming the floating slag off the top of the ladles. This technological shift noticeably reduces the overall headcount required down on the dangerous floor, but it fundamentally and permanently shifts the basic educational requirements of the high-paying job. The modern, newly hired steelworker is now very often just as much a highly trained computer technician and a complex systems analyst as they are a traditional heavy machinery operator. The industry is actively trying to improve overall working conditions, not just out of strict regulatory compliance, but because highly skilled, reliable technical labor has become exceptionally scarce across the country, and actively retaining that valuable human talent is absolutely essential for their long-term corporate survival. The integrated steel mill permanently remains one of the absolute most profound, terrifying, and beautiful achievements of modern human engineering. A sprawling, deafening place where raw, dirty earth is miraculously transformed into the heavy, unyielding foundation of our modern civilization through a relentless, continuous flow of extreme heat, precise chemistry, and massive mechanical force. It is an industrial environment that is undoubtedly much safer, far cleaner, and significantly more highly regulated than it was a single generation ago. Yet it still absolutely demands a high level of physical endurance and constant technical vigilance that very few other modern professions require. You simply cannot stand next to a humming, glowing vessel containing 200 tons of churning liquid iron and not feel a deep, abiding respect for the regular people who control it. If you enjoyed this, subscribe to Industrial Enigma for more like it. And if you have ever worked a shift inside a plant like this, or if someone in your family did, drop it in the comments below. I would genuinely like to hear it. Thanks for watching.